Good morning. Welcome to part 3 of our video notes on batteries. And in today's video, we are going to address how to determine Gibbs free energy. Yeah, I apologize for all the sun that was in part 2. I went ahead and waited about 30 or so minutes, 40 minutes, and the sun's moved a little bit, so now we don't have that huge glare. So let's go through and talk a little bit about what is Gibbs free energy. Gibbs free energy is the mathematical expression that allows us to determine whether or not a reaction is spontaneous. That reaction can be any thermochemical reaction, whether it's producing or absorbing energy. If you find out and calculate that your Gibbs free energy is going to be if Gibbs free energy is negative, then it is spontaneous. If it is positive, then it's not spontaneous. Now, in our last video series, we talked about the cell potential. We said if the cell potential was negative, it's non-spontaneous. Well, the cell potential and the signs of the cell potential and Gibbs free energy are just the opposite. So remember that in Gibbs free energy, if delta G is negative, then it is going to be spontaneous. Okay, let's go through and look at the example problem that I have for you. So it says, using the table of standard reduction potentials, calculate delta G for the following reaction. So what we really have to make sure that we understand is what is the formula for delta G, and I have it up here. The formula is negative NF of the cell potential. So we know we're going to have to calculate the cell potential, so we're going to do that. What is F and what is N? Well, F is going to be, and if you look over here, that says Faraday's constant. And in our resource packet, the AP resource packet found on our resources, it does have this listed. So that'll always be available for you. And it's 9.65 times 10 to the 4th. And then if you look at the N, what is the N? The N is going to be the number of moles in your balanced equation. So what I want to do is I need to go through and write down the half reactions and make sure it's balanced. So I'm going to go through first and just simply see what's being oxidized and what's being reduced. So here we go from a positive 2 to a 0, so I'm gaining electrons. So that's GER, so that's being reduced. Here I'm going from 0 to positive 2, so I'm LEOing, or losing electrons. So that's going to be oxidized. So let's go through real quick and just set up our half reaction. So I have, number 1, I have Cu plus 2 yields Cu, and then number 2, I have Fe, and then that's going to be yields Fe plus 2. So on this side, I'm going to have to add 2 electrons to get the charge to be 0 and 0, and I have to add 2 electrons on this side to get 0 and 0. So guys, do you see how my electrical charges are equal? I didn't have to find a least common multiple or anything. So if they're equal, I could combine them, and everything is fine because the charges are negative 2 electrons in my reactant, 2 electrons in my product. That is my mole number. So whenever I do delta G is going to be equal to negative N F E of O. So I'm going to go ahead and start plugging my numbers in. Delta G is negative, and that's going to be 2, because we just found that the number of moles is 2. And then I'm going to say 9.65. I usually always round off to the 3 sig figs. And then I need to calculate my E of O. So I'm going to come back over here, and I know that my cell potential is going to be the potential of my what is being oxidized plus the cell potential of what is being reduced. So when I come back up here and I look at my Leota line says GR, then it says that my GR is what is being reduced, and that is my copper. So I'm going to add 0.34. What is being oxidized is my iron. And do you see how I wrote down up here? It's straight off of the standard reduction table. I wrote its reduction. Well, we know that if we have to flip this over to make it oxidized, then the sign is going to change. So it's going to be 0.44. So now when I add these two together, I get 0.78 volts. So I'm going to come all the way back over here and substitute that E of O in for 0.78 volts. So now my delta G is equal to, and it is negative 1.51 times 10 to the 5th. Now, the units for this, I'm not going to worry about it because it would just be joules, because it's all energy, and your energy is measured in joules. So everything cancels out. I'm not worrying about keeping up with the units until I get to the very end and just put joules. So the original question says, is this reaction spontaneous? If my delta G is negative, then the answer is yes, it is spontaneous. All right, so I hope that that has allowed you to see how we use delta G, Gibbs Free Energy. It's not a very difficult, and two of the numbers are pretty much standard. You have F, which is a constant, and then the number of moles. I guess that would be the trickiest. You have to balance out your half reactions to do that. Other than that, I think that you now have, with these 3 videos, enough knowledge to go through and finish all of the lab if you haven't finished that, and I have a couple of practice problems for you. All right, thank you.